Hola chamas y chamos, welcome back to Álvaro de Labs. It has been a while since the last time I put some 3D content on the channel, so I thought about giving an update on the Modern 3GS tutorial that we did the last time, where we created a 3GS application to show some 3D objects using Vite. This video tutorial is a little bit more advanced than the previous one. We're gonna touch topics more complicated like shaders. So if you're still catching up with 3GS and how to add materials or objects, etc., check the previous video. But first, some word from our sponsors that made possible this channel. This video is sponsored by Storyblock. Looking for a CMS solution that is great both for marketing teams and developers? Look no further. Storyblock is the headless CMS solutions that you always wanted to have. See how easy it is to change content for your website with a real-time visual editor, creating a delightful customer experience for your teams. Go from a content update to production in no time. Storyblock is easily integrable with multiple tech stacks, making your dev team's life easier. Go and try it for free at storyblock.com. Let's go! So this is what we are going to build today. If you remember, before we have a sphere, and this version the sphere has some kind of waves, right? And this is all done with the shaders that we're gonna see today. How to move the vertex and also change the colors of the sphere so we have this cool gradient effect with the UV maps. To start real quick, we're gonna use the boilerplate that we created in the previous tutorial, which is called Modern 3GS. So to do that, we go to our terminal and we just need to put npx digit, which is like a package that makes a fancy git clone. And then you can work with GitHub template. In this case, the project that I have, Modern 3, is a GitHub template and you can download it and copy it. Since this boilerplate already has the functionality to add GLCL shaders, we are going to use a specific branch that I created just for this tutorial without any shader support because we are going to write it from scratch. Okay, so make sure you are using Alvaro Modern 3 numeral feature without shader support. Okay, and we're going to call it Vite shaders. So it's gonna say it was cloned. Let's open it. Okay, so now let's use the default installation for PNPM. Okay, so we have our Node modules, and I have an extension that automatically opens the Vite app just in VS Code. But I figure out that using 3GS and any 3D, the frames per second are really low when using the IDE, so we're not gonna use this feature for this. Let's take a quick look at what this boilerplate brings. So we have a scene, a simple scene with a sphere, okay? It has a tune material, I can see it because of the shadow. And we have this tweak pane that allows us to change the position of the directional light. So here we can change like the X, the Y, etc. Okay, if we take a look at the code, we have a main TS here that contains all of our 3GS instances and classes. So we create the ambient light, a directional light like this, then the sphere material, which is a mesh tune, as I said, and we put on our stuff like the cast shadows to be able to see the shadows, which are especially nice when you're using the tune materials because it looks a little bit like Genshin Impact. And then we have the tweak pane configuration and just basic rendering and frames per second graph. Okay, so we're gonna work on top of this to create the shaders. But until now, you may wonder, what the is a shader? People tend to get really nervous when talking about shaders, but it's just not that complicated. Basically, it's a program, a computational program, like it could be JavaScript, Python, whatever, that is written in GLSL. Okay, that's the extension. As in any other program, you run it, and then this is sent to the GPU, the graphic processing unit, because we are talking about graphics here. We want to do a geometry in the scene, right? So basically we need to send two types of data. One is the position of each one of the pixels or vertex or fragments that our vertex is gonna have. Let's say we're doing a square, right? So we are putting here 4 vertices, and this is information on the position that each one of them are there. This is what we call the vertex shader. And I cannot write with this, so I'm gonna redo it because it looks pretty bad, and it's just gonna say vertex. Okay, this is one type of shader. Oh, let me remove the fill here because also looks really off. Okay, this is one kind of shader, and we have another kind of shader. So I'm going to replicate this and put it here, as the other one is going to receive the data, okay, from here. And what this shader is going to do is going to tell us for each fragment here. And when we talk about fragment, it's like as the smallest unit. Think about it as pixels, okay? But it's not quite the same. And in this case, with the fragment shader, what we are going to tell the geometry is how it's being colored, or what material does it have, how the light reflects on it, etc. So think about it as the colors that this geometry will have, okay? So we have the vertex, which is the positions, and then we have this one that I'm going just to do the same, and let's put it a name. This is gonna be the fragment shader. Okay, if I can write, this is gonna be the fragment shader. Why creating our own shaders? If we have, for example, 3ds that already give us specific materials, geometries like the sphere and so on, it's because there is no material in 3ds that allows us to create things like this. So when you want to do something that is really performant, okay, that is plain simple, and because this is not as complicated as you might think, okay, and it will be really tough to try to simulate something like that with the existing classes that 3ds gives you. So the shaders gives you freedom on manipulating the vertex and the colors in the way that you want. Basically mathematics. And also it's amazing for processing. Let's create some shaders. So let's go around here when we have our objects, and I'm gonna create another material. This is gonna be called shader material, and it's gonna be a raw shader material. Inside of it, we're gonna have the vertex shader, which is the one that controls the position, and we're gonna have a fragment shader, which is responsible for the colors. Okay. Also, let's add wireframe. For now, let's use it on the sphere. So I'm gonna replace the sphere material for the shader material, and let's see how it looks. So for now, it disappeared because we are actually not passing any info into the shader. So what we will need to do is create some program here. We're using template literals because we will need to create code, okay, and we need to enter in several places, okay. So in this part, don't try to understand what I will write because I will explain it afterward. Just trust me and copy and paste, okay. So we're gonna put uniform mat4 projection matrix, uniform mat4. Mat is a matrix, okay, so it's 444. View matrix, and another one for the model. Then we need an attribute, which is a vector, okay, a vector of 3 x, y, and z position. And then we create the main function, and we have something called GL position, which is a variable that is already defined on the vertex shader, and it's basically going to be the projection matrix multiplied by the view, by the model, and by a vector 4, which is a position plus 1 another. I understand it's weird, okay? We will see how it works. So let's go to the fragment shader, and here you're gonna define a precision high P flow. I'm gonna put it to medium because it will affect the performance, but in case you have a strong machine, go for it. Here we're basically going to define the color of our material, okay? So there is, same as the GL position, there is a GL frag color, which is a vector 4. It's important that every float you put it with the dot, okay, because if not, it's gonna throw an error, okay? And in this case, let's put the same color that we have, the teal color. So the teal color is gonna be something like zeros, RGB. This is RGB, okay? This is red, green, and blue. So this one is gonna be 5 also. Let's save. And you see that we have again our teal color. So this is how basically you can recreate the same that we were using with shaders. Let's now explain what is inside in each shader, okay? So let's go to the vertex shader, and we have 3 lines that are called uniform math form. So uniform is basically a way of passing data from JavaScript into our shader, okay? Mat4 means matrix, okay, a matrix of 4. And we have 3 of them. We have the projection matrix, the view matrix, and the model matrix. The model matrix contains all the information about the mesh and how it transforms. So every change of the scale, rotation, and position is going to be handled by the model matrix. The view matrix is something similar, but it's related to the camera, so how the camera moves around the object, or how the object looks when you change the camera position, for example. And the projection matrix is just basically, it will transform everything, all our coordinates, into the final clip, okay? To see how it works in practice, let's separate a little bit. So I'm going to do something like this. I'm going to create a vector 4, okay? And it's going to have the model position. And the model position is going to be exactly this part here, okay? So we can remove it for the last one. And multiply by model position, okay? So now if we add model position, and let's say we want to change like how high it is from the plane, right? We can do this, and let's put a number like 4 and save. It's gonna throw an error because every float you will need to put it with .0, okay? And we are talking about position that are floats, so we need to put the .0, okay? So you can see now our sphere is way up, so we change the position of the sphere with the model position. Like this. We can also change the view position. So the view position is just basically the view matrix, and it's gonna be multiplied by the model position. So in the final one, let's change this for view position, okay? So if we change the view position, and let's say we change it on the Y again, you're gonna see that it changed, but it changed because of the camera, okay? Let's put something more drastic. Let's put like 8. again with dot zero to avoid any errors. And you will see that now related to the camera, this is way off. Why this remains the same? Because we actually didn't change the properties on the shader of the plane. So it's only affecting this one, okay? For the next part, I'm gonna just hide the sphere and I'm gonna apply the shader material into the plane because it's gonna be easier to explain all the topics in the plane before we go to the sphere, okay? And I just commented it here, and where we have the new tune material for the plane, let's use the shader material. Okay, so now we see that it's applied to the shader material. Let's show how powerful modifying the shaders can be. So until now we were like playing around with the model position, but we can do amazing stuff with it. Let's say we have this as the seafloor, right? And we want to create some waves. So we need a mathematical function that allow us to create waves. So if you're familiar with trigonometry and stuff, then it's an easy answer. You can use a sine wave. For all of you that doesn't know what a sine wave is, it's just basically a mathematical representation of a function that can create these kind of waves, okay? That they go from 0 into 1 or minus 1, okay? And then you can multiply it and change the amplitude of it. It's called amplitude. Then we have the frequency, which is how often they do the crest, okay? How often this be. Maybe if I add another, like, okay, we can show it like this. So if I add a major frequency to this, it's gonna do something like this. So it's gonna be the same sign, okay, but more stretch. I don't know if I explained it correctly, okay? Let me know in the comments if you have any doubt about sine waves. We're gonna use that for all shaders. So here in the position, model position, we're gonna increase the y with a sine wave. So it's gonna be my plus, okay, and use the sin, okay, which is a sine wave, and we're gonna use the model position x. So we are gonna modify the y, the height, by the x value, okay. So if we see here our plane, this is the x-axis and this is the y-axis, okay. So we're gonna modify everything in this axis by how it's going in this one, okay. And we are gonna multiply by the frequency. So in this case, I'm gonna put an arbitrary number, okay, and then by the frequency, sorry. And here is gonna be the amplitude. Okay, so let's put a really low amplitude and let's click save. So now you see that somehow like a really choppy waves are being created here. If I add more here to the amplitude, so if I increase the amplitude to, I don't know, 2.0, you're gonna see that now the waves are way more intense, okay. I don't know why it's so choppy. Maybe it's because the amount of here the segments that these have. So maybe if I increase the segments, it's gonna have a better. Okay, doesn't seem like it. Let's see what happens if we change the frequency. So let's put our way lower frequency. Okay, this is better, and it is way more smooth. Also, you can see this effect because we're using a plane and we are not checking the other side. So I think there is something that we can put on the shader material just below, okay? That is called side, and let's put it to double side. Okay. Okay, now it looks a little bit better because we can actually see the whole thing, both sides. So that's cool. Also, we wanted to check how this is created, because what basically WebG does in Three.js is just convert everything to little triangles and put it on the canvas, right? So if we put wireframe to true, we're gonna see all those little triangles like this. How cool is that? Okay, so until now we have put in everything here hard-coded, okay? So let's go back to the uniform topic. So uniform is a way of passing data from JavaScript into your shader. So what if we use it to pass from the tweak pane? We can create some controls here and say, okay, let's change the frequency and the amplitude. How we can do that? We go here and we in the shader editor. Okay, we are in the shader material. We're here in the raw shader material. Okay, and we add the property uniforms. And in uniforms, we are going to create one that is called frequency with this value, and we are going to create another one that is amplitude. Okay, with let's put in way less, like 0.1. Okay. Let's save it. For now, nothing changed. Let's now add it here to the shader. Okay. So the way of doing that is we are going to create another uniform. In this case, it's going to be a float, which is going to be U frequency. And this one, uniform float U amplitude. Why I put a prefix of U? Because you will see afterwards we are gonna use another thing for the fragment shader, and it's gonna use another prefix. So this way we can say that this one, the frequency is uniform. Okay. We're gonna change it here. So it's gonna be U frequency, and here is gonna be U amplitude. Okay, cool. So if we save, we're probably gonna see something different. Let me check the inspector, maybe there is an error. So yeah, there is an error because I missed the semicolon here. You need to be careful about the semicolons. Okay, now we can see it, and since the amplitude is really slow, so just doing a little way. Okay, let's add the tweak pane here in order to see it. So I'm gonna just we're not gonna do anything with the lights, so I'm gonna just comment it. And we have an object called give, and we are gonna add a folder which is gonna be called title X. You're gonna see why in a moment. Expanded, and this is gonna be equal folder X. Okay, and to this folder X we're gonna add an input, which is gonna be shader material uniforms frequency value. Okay, and this let's put the label of frequency, not in uppercase, please. Yes, we're gonna put a minimum of this, maximum of that, and a step of 0.1. Let's save it and see if it's actually working. So if I change here, you can see that it changed the frequency of the waves. Okay, so the more I get, if you remember the explanation before, actually I'm gonna remove the wireframe, or at least make it toggable, so we can add to our GUI add input shader material, but it's gonna be wireframe. Okay, Let's save it. And we can put it as false at the beginning, so we can toggle it whenever we want. Okay, perfect. So we toggle here, we can see the wireframe. I love how the tweak pane works because you can actually add anything you like and you can control everything to experiment. Okay, so maybe the frequency we're gonna put it like, I don't know, maybe 5, okay? That looks better. And if you remember the graphic that I showed you before about the waves, it's something similar, right? So it goes into one point and goes to another. So if we put 1.0 here, for example, we can see that it's a choppy version of what I draw, okay? So maybe let's reduce it again. Let's put 0.5 so we have something fancy. Oh, I have so much allergy, sorry. I wake up in the morning with a lot of allergy, I don't know why. Okay, so let's add another one for the amplitude, okay? So this is gonna be amplitude, and this is gonna be U amplitude. And how about that? Now we can change the amplitude right away. That looks really cool. Cool. So this way we can pass things from the JavaScript into our shader. But this looks a little bit stiff. It's not doing anything. It's not moving. Let's make it move. So to make this bad boy move, we will need something special. So we will need another uniform, and we're gonna call it uTime. It's gonna be a float with a value of 0. Okay. So what do we have in our application that can actually send the time? Okay, so a difference between time. So to do that, we can go to the loop, right? Because this is running like every request animation frame is gonna create another loop. So there is a way on Three.js to actually measure the elapsed time between one and another. So we're gonna use clock. Okay, so we define it like this: const clock equal new tree clock. And inside of here, we're gonna say const elapsed time is equal to clock get elapsed time. So this is gonna be the difference between them. Oh no, that's the delta. I think elapsed time is all the time passed from the beginning. I think. I don't remember quite well. Yeah, here, get the second passes since the clock start. Okay, that's fine. My bad. But how we can pass that to the uniform, or how we can modify the uniform? As any other object, we can use shader material uniforms dot uTime dot value and assign the elapsed time. Let's see what happens if we save. Ta-da! Nothing is happening because we didn't add it to the vertex shader. So let's do that. Let's go here, uniform, flood uTime. And how we use it in the sine wave is basically to, we subtract it from the frequency. So you put in here, minus uTime, and now you can see that it's moving. It's moving through time, which is kind of cool. Of course, you can increase the speed if you multiply any other uniform for this, but you already have the frequency, so you can do it with that. But this is how you can make it move. So now we saw how to use uniform to change some variables in the shader material vertex shader, but can we do the same in the fragment shader? Let's figure out. So let's say we're bored about this teal color and we want to be able to change it here. So to do that, we can create another uniform, which is gonna be uniform. It's gonna be U color. Okay. And for this, I'm gonna use this class here, tree color, because it gives you the RGB values right away to be used. So let's put hot pink, okay? Nothing is happening because we need to go to our fragment shader and say, okay, we have another uniform, which is called, in this case, I think it's gonna be a vector 3. Okay, so it's U color. And here we have the fragment color, which is RGB, and I think this is the alpha. I'm not really sure. So we can do something really cool with this because we already know that this is a vector tree, so it has a RGB. We can remove this tree here and just put U color, and let's see what happens. Now we can see that the color has changed. Why? Okay, we can do exactly the same by using U color R, I think, U color green, and U color RGB. Okay, B. If we save it, it's gonna be the same, but I really like this feature of this language that you can actually put U color and forget about the rest. So this is a vector 3. I had to remove these 3 bad boys here. Okay, let's keep it like this. So let's change this with the TwigPaint, right? Let's go again around here, and we're gonna add an input. Add input, shader, material, uniform U color. And I think I don't have to pass anything else, or maybe I do, because it's showing it really weird though. Here.
So much later that the old narrator got tired of waiting and they had to hire a new one.
Okay, I think I solved it. Basically, it doesn't work quite well with tree color directly if you put it in the TwigPaint. So what I did is a little bit of a hack. I created an object, I put the color in hex value, and we are passing that instead of the hot pink here. You can pass a X value to the tree color, okay? And here on the input, instead of using shader materials uniform U color directly here, we are reacting to the change on the shader props, okay, which is gonna be this one. And on change, we are gonna pass a new tree color with the value, okay? So if I here change the color, you can see that it actually changed, which is cool, okay? If you have any questions about this part, please let me know in the comments. I will explain further. It's basically we add another object, we react to that object, and we pass an assign to the shader material because the TwigPaint and the format that the shader needs weren't the same, okay? Now let's talk about a more complex topic, which is UV mapping. So if you are familiar with 3D, you probably already know what UV mapping is. If you haven't, I will explain it real quick. So each geometry, okay, has a way that you can project a bidimensional plane texture, okay, into the 3D object. What the hell is that? Okay, so you remember when we were kids, probably did this cube with paper, like you cut carton or paper and you managed to do this form, right? So basically it's the same concept. If you disarm this cube and you put it on the floor or on the table, it's gonna be in a bidimensional plane that is gonna have a height and a width, right? So that's basically what a UV mapping is. It's just taking the 3D shape and put it on a bidimensional plane. In this case, the cube, we unwrap it and we put it on the plane. And to not confuse with X and Y that is already used in 3D, they come up with a U and V notation. I think U is X and V is Y, but I could be totally wrong, okay? This is also applies, for example, the candies that you have as a kid, where you have the form of, I don't know, Santa Claus, Saint Claus chocolate, and when you take the wrapping off and you put it like straight, it's gonna deform all the face of Santa Claus and stuff. So it's exactly the same concept. Why I'm explaining this part? Because we can actually use one of the attributes that come with each geometry to put some colors. Instead of U color, we can use the UV map, okay? Because it adds some debug colors so you can see the difference in the geometry. Let's go back to our geometry here, and I'm going exactly to show you what I mean. So we have our plane here, right? If I add just below plane console log, and then probably need to do it to the geometry, okay? So I'm going to use this as a plane geometry, okay, like this, and we pass it to the mesh, okay? We cannot do it to the mesh, we need to do it for the geometry itself. So in attributes, there is one attribute that is the UV, okay? If we check the inspector, we're gonna see something really weird. That is basically, this is a float 332 buffer attribute, and it's an array of a lot of values, okay? This doesn't help that much here, so let's see a way of seeing visually, okay? So we know that we have an attribute here. We can access attributes only in the vertex shader. So here we can say attribute is gonna be UV, no, it's gonna be a vector too, sorry, UV, okay? And something cool that we're gonna do is that there is, as we have uniform as a specific way of passing data from JavaScript into our vertex shader, we also have one to pass things for the vertex into the fragment shader, which is called variant. Okay, so we need to define a variant here. And remember that we talked about the naming convention, right? That was using U for U frequency, U time, etc. Here we are gonna use V, and we are gonna pass, it's a variant that pass the UV. Okay, we're gonna use it right here, and we're gonna pass the attribute from. I know it's a little bit like why we need to do that, but basically understand that the fragment shader doesn't have access to the attributes because it's something about the geometry. Okay, it's about the positions, the rotations. It's not about the colors. Okay, and if we pass it to our fragment shader, we need to define here also that we are going to use a variant. Okay, this is what is going to serve as a bridge between the vertex and the fragment shader. And instead of view color, we can use here our VUV. Okay. But since VUV is a vector 2, we need a third value here, which I'm going to keep it at 0.5. And look how cool it looks. So basically, this is like color information of the geometry that goes from different colors to understand where it's fit, okay? In this case, if we put the plane like this, we will see the same concept that we were talking about the UV unwrapping. So this is the UV unwrapping on a plane. Remember we have a sphere, right? So let's get back our sphere just to show that every geometry has their own, okay? Let's get back this sphere right here, okay? And instead of 10, no, we're gonna pass the shader material here. Okay, perfect. And now you can see also something really funny. It's because we're using the same shader, and the shader does have some animations here, right? We are modifying the model position with the amplitude. So if I remove it just real quick, we're gonna see our original geometries without any change. And look at here. This is the UV unwrapping of the sphere. Okay, you can see that actually in certain point it cuts, right? It looks like different here. Okay, because this is the UV unwrapping of a sphere. You can do it with a cube, you can do it with whatever geometry do you want. So this is pretty handy. I use it a lot whenever I don't have any textures and I don't want to worry about the color, but I want to see how it will look in the final object. I use this kind of debug colors from the UV. And it looks kind of cool also. So until now, we have learned how to use the vertex shader to create different forms, modify the position of our geometry, and also create kind of cool waves using the sine wave. Also, we learned how to pass uniforms to control the amplitude and the frequency of the sine wave to make different forms. And also we learned about color in the fragment shader and how to use the UV map to color it, right? So let's put all that knowledge together to achieve our final result, which is this one. As you can see, it's a sphere with a UV map, but it's doing like a certain waves inside, okay? So how can we achieve that? First, we're gonna do is going to the vertex shader. And until now, we have used the U frequency as a float, but we can use it as something different. We can actually hold the values for different frequencies in the X and Y, because we're gonna change the way we are modifying the model position. So if I use model position C and use this right here, model position, you see frequency, and then we can use model position C, but instead of using the model position X, we're gonna use the Y. And we can change to cos. So cos is another function that is exactly the same as the sine wave, but let's put another color here, okay? It starts from here. So in the time 0 here, it has the value of 1. Okay, so this is what we call shift. So this is the cos. And this one, the green one, is the sine. Okay? So we're gonna use that one. And you can already see that it's doing super strange things here, like an abstract. Okay, let's see how we can make it a little bit better. Right now we are modifying the C axis, which is the blue one. I don't know if you can see it here, but this is the C, this is the Y, and this is the X. So it's basically modifying how the theta is based on a sine and a cosine, okay? But we want a more like wave effect also in the X. So to do that, instead of modifying the theta value, we're gonna modify the Y and the X using the contrary model position. So for the Y, we're gonna use the X, and for the X, we're gonna use the model position Y. Let's save it. And now we can see that it's actually too much. If we reduce the frequency, we can see that it looks like a blob, right? And we can actually put something like this. So it seems like it's floating, which is kind of cool. It looks really fun. Okay, but the problem here is that both of them are resonating at the same frequency. Okay, so one way of solving this is that we can convert the amplitude and the frequency into vectors. So I'm going to put vector 2 here and vector 2 here, and I'm going to use for this one the X, amplitude X, frequency Y, and frequency Y. Okay, But it's not gonna work because we are actually passing here in the uniforms a float value. So how we can change that? We can use vectors. To use vectors here, basically we can do this. New 3 vector 2 and some values. We're gonna do exactly the same for the amplitude. So we're gonna copy and paste this here. And now let's put something like, I don't know, 0.1, 0.1. Because I want the frequency on the G value different, or for example the X value, let's put 20 and this one 5, okay? We will need to modify also our folders here because we are changing the value, but it's not longer gonna be the value. It's gonna be value, and this one is gonna be the X, and this one is gonna be the X. That's why I put it on a folder, because I'm gonna copy and paste these two here, like this, and I'm gonna create another folder called Y. So folder Y, and here is gonna be Y and Y. Oops. Okay, we have something a little bit closer to what we need. So we have the frequency here, we can modify it, and we can modify this one here, which creates more like, ooh, nice. Okay. You can play with it until you have the result that you want. In this case, let me check the variables that I used in the other experiment, so we can have a closer one. So I think for the amplitude, I use a really low amplitude, which is like 0.5 and 0.5. Ooh, no, 0.5. Too much. Okay. Okay, something like that. And for the frequency, I think I have a less frequency. I have like, for this one, the top, okay, I know the problem here. The frequency, the maximum, let's put it at 100, okay? Let's put it at 100. Okay, now it's better because we can actually add more frequencies. So yeah, look at that. I'm gonna put it on full screen. So we can change the frequency of each one. And when you change, you have X and Y frequencies, start having like waves. It's not only one direction, like we will have it, not pun intended, on the plane that was doing the sine wave, but right now we have it also in the other axis. So it looks kind of cool. It looks like a video game kind of portal, something like that. If we change the amplitude, we can make it more exaggerated or more fluid, something like that. I prefer to put it like really low because it looks really good like this. And that's pretty much how you can use vertex shaders to create something like that. But until now, we have done it in a really tough way. A lot of information, a lot of... Is there a way we can do this easier? Let's figure out. So there are two things that we can do to improve this. We have been using raw shader material. Okay, this is the basic one. But there is another shader material included in 3GS, which is called shader material. Let's see what happens if we change it right away. It's gonna crash, okay? But more important, why did it crash? Let's see the developer tools to debug why it's failing. So it's saying that there is a redefinition for projection matrix, view matrix, model matrix, position, and UV. What does it mean? Basically, when we are adding shading material, we don't need to declare all of this here. This comes by default. So we can remove it, also these two, okay? And I think on the fragment shader, we can remove this one here. If we click save, we don't have any error and we have our object again. So since it's a lot of things and you don't want to repeat every time, the same thing, like uniform model matrix. You can use shader material directly, which is what I use often, okay? But until now, we have our programs here in the text, okay? This is a string, basically, okay? We have the fragment shader and we have the vertex shader. That's not optimal. What if I told you that we can have a file that we can import into our scene with the vertex shader and the fragment shader? So these two, the shaders in general, have an extension of GLSL, which, let me see what it was, the meaning of it, GLCL. You have, So GLCL is a C style language, that's why the notation, and it's called Open GL Shading Language. Okay, that's the meaning of it. So we can create some shaders here in our folder. So if I open the file extension here, I'm gonna use the full screen, right? And we go to, this is our main TS, which has our program. We can create a folder called shaders. And inside of it, let's create a vertex, ELCL, and another one called fragments, or fragment, ELCL. Okay, so right away, let's copy and paste these two here into the corresponding file. Okay, it's important that you keep the indentation. I don't have auto formatting for this. Okay, and for the fragment, let's cut this here and put it here and correct the indentation. Save it. And right now, let's remove the template string, put it like this. Okay, and let's import it from the folder of the vertex shader from shaders, vertex, and fragment from here. Okay, let's save and see what happens. So it's gonna throw an error, and the reason is that we go to the DevTools. It's gonna say that unexpected identifier vec2. And that's because we are trying to add to Vite GLSL. We cannot do it by default. There is no support for it by default, but we can use a plugin called Vite plugin ELCL to use this kind of file. I'm gonna create another terminal here, and basically I'm going to install it. So pnpm add Vite plugin GLSL. Okay, now edit, let's go to vite.config, and we're gonna add a plugin. So this plugin is gonna be GLCL like this, and we can import that from Vite plugin GLCL. So let's save it and let's see if it works. Ta-da! It actually worked. So with this we can use shaders as files, okay, and just importing them into our scene and using in the shader material here. So if you can see, it's way more practical and way cleaner. And that's how you can load shaders into your Three.js application using Vite. This opened the world of possibilities in terms of what you can achieve with Three.js. It requires a lot of practice. There are books dedicated only to shaders, so I will put a lot of resources here on the description in the channel, plus the repository with the code. I'm really looking forward what kind of things you can create with this. Please share it with me in Twitter, and if you have any questions, just put it on the comment section and I will be more than glad to help you. If this video was helpful for you, don't forget to subscribe and drop a like. See you in the next one. Ciao!